In the previous animation stream, we were fixing problems with the animation system, and we were successful in doing that. But along the way, we noticed some other things. Like, for example, this piece of code here is the thing that concatenates transforms from like the local space, the space of each bone, into the object space coordinates that we can then use to render the mesh. And we're doing it in a kind of a stupid way where we get this whole matrix. That's a 4x4 matrix with 3 of the elements that we know to ignore. So it's a mostly 4x4. And then we just get a new Xform state out of that matrix, which is it's messy. Like we can look at we do that for 2. So actually, sorry, this turns this Xform state. Okay, so that I'm not babbling too much, let's look at what the Xform state is. That's in the sampled animation. So we represent the transformation of each bone as one of these things. It has a discrete translation, orientation, and scale. This is the same kind of information that you would have in a transformation matrix, but it's a more convenient form. It's easier to understand, especially the rotation part, but it's also cleaner to interpolate, because the thing is that rotations don't really interpolate the same way as translations or scales. So when you factor things apart this way, then interpolate them, and then combine them later, you get a result that makes more sense than you would otherwise. Okay, so that's why we use this representation. Well, there's potentially other reasons, but we're about to do away with some of the other reasons. Anyway, oh no, we're not about to. We'll explain in a minute. Anyway, so we use this representation and not a matrix to perform our intermediate operations, right? So that's all fine. And then, but when we want to generate a matrix, what we're doing right now is we're getting a matrix for this guy, getting a matrix for this guy, doing a matrix multiply, and then setting the result. And so set from matrix, I think that's back here. Yeah. We call this get orientation routine to turn, well, first of all, we're cheaping out and saying that the scale is, only a vector 3, which we're probably going to change in a minute. But then we do this get orientation, which is all this stuff, right? To get a quaternion out of a matrix. And it's like, why are we doing all of that math? It seems like a lot. On top of the 4x4 matrix multiply and then all this stuff. So the point is, what we did in this other stream is we started simplifying that. We said, hey, well, the translation of the, so instead of doing the matrix multiply to generate the resulting transform, we can just do some math on a piece of paper and figure out how to turn or how to factor 2 of these transform states together, essentially, writing down what the multiplication operation would be of one of these times the other, right? And so for translation, that's pretty easy. For rotation, it's pretty easy. For scale, it was not so easy because our scale representation didn't have enough information in it. We were also doing it wrong. We were doing it wrong, but it also didn't have enough information in it. So, well, okay. there are two issues that we're gonna deal with. Okay, so one is that the scale that we were representing before was only what would you call it? A uniform scale along each dimension of the coordinate system that the scaling is in, which was the node scale. So what even does that mean? Well, I don't know. Like if you just, if you visualize a transform in some arbitrary orientation, which is like where this bone's coordinate system is, then you get one factor along each axis, right? And that means that when you represent this as a transformation matrix, it's a diagonal matrix. That has some nice properties. The thing is, it may not necessarily represent all animations that we want to represent, because some animations will use maybe shearing, or some animations may be scaling, but in a coordinate system that doesn't line up with the node's coordinate system. You're not really in control of what people do. Now the thing is, our sample data, like here's one of them. Our sample data right now, here's the list of all the bone names, and here's the transforms. Here's position, orientation, scale, shear. Position, orientation, scale, shear. So you note I didn't output 3 numbers. I outputted, how many is this? 9, right? This is actually a 3x3 scale shear matrix. And right now we're ignoring most of the information because we just decided not to support shear yet. Shearing is sort of what happens if you just like grab part of a thing and stretch it in a weird way. It doesn't typically look good if you do it naively, but subtle shearing may be part of an animation effect that people do, right? We decided not to support that, and so when we load this, we're just grabbing essentially these 3 ones. Now, I think for all our data, this entire line is the same every time for every animation, right? So our scaling is essentially does nothing, right? It multiplies everything by 1. So that's why I'm saying we weren't even doing this right before, because you wouldn't get an invalid result, because this is actually like, we could just say this hard code the scale is 1 and it would be correct, right? We don't, like, we should be able to get that result by doing the correct factoring through here. And we'll go look at the math of that again in a second in order to make it make sense. So there's 2 orthogonal tasks that we're going to do. And I think we may just do one of them today and then the other one later. So one of them is just getting this path turned on. This do not go to matrix dummy is turned off right now. Getting this path turned on so that we can combine these Xform states together without going to a 4x4 and back and doing all that ugly stuff. And then we can get rid of this and maybe some of those helper functions down below, and that'll be nice. We should be able to do that independently of anything else. Then, maybe next stream or sometime, we want to implement different levels of support for scaling. So, here, if you look at how many numbers we have here, we have 3 for the position, 4 for the orientation, that's 7. And then we have another 9 for scale shear, all of which, those 9 are doing nothing, right? They just say, do nothing to the result. So over half our animation data says do nothing, right? Now, you might say, well, some of the nodes in some animation might have a scale shear that's not a do nothing scale shear. And that's true. But we could detect those and we could flag each individual node. So here at the top of this animation file, we say what the bone names are and who their parent is. We could also have a line here that says flags And we could put some flags, and one of those flags could be no scale, right? Another flag could be uniform scale. Well, no scale means the whole scale is 1, so don't bother. Another flag could be like uniform scale. We just have one number instead of 9. And that number is allowed to balloon or not balloon the whole transformation matrix, right? We could have a version that's 3 if we think that's worth doing. And we could have a version that's all 9. And because we would flag that on a per node basis, then most of these, almost none of these numbers would ever be necessary. So that makes loading faster, and it means that in memory, you use a lot less memory to represent these things. Now that said, we're still doing a really uncompressed representation because, so this animation file, for example, is at 30 frames per second, which means every one of these, how many did we say? 16 numbers. Every one of these sets of 16 numbers happens every 1/30th of a second. This textual representation is especially inefficient, but even if you convert it to a binary representation, it's not a really efficient way to store animation data. So sometime later we may look at compression in some way. But, for now, we're just more thinking about the very low-hanging fruit of like half our animation data being wasted. So that's the other half of what we're thinking about here. And that may happen next stream, for all I know. All right. So that is, I think, everything to talk about. Okay, we can talk about the math behind this situation. So we have, again, we spent some time in previous streams figuring this out again, but we have this Xform state. Let's go back and look at that. What file was that in? Sampled animation. So we have this Xform state. It's got a translation, an orientation, and a scale. We're just going to call, these are slightly different letters than last time, but we're going to call this T. The transform that this represents is going to be capital T. This is going to be capital R for rotation, and this is going to be capital S. And they're actually in a different order. So to perform this on a vector, we would go translation times scale times rotation times V for the vector, right? And these are column vectors. So, if you were to do this one at a time, first you would multiply the rotation matrix times the vector, and then the scale matrix times that resulting vector, and then the translation matrix by that resulting vector. Of course, part of the whole reason this representation is nice is we're not really going to represent the translation as a matrix multiply because it's just 3-number add, and we know that, right? And rotation as well, we don't have to go all the way out into a 3x3 matrix to rotate the vector because we know how to multiply a quaternion by a vector directly, and it's more efficient. For one transform, it's more efficient. Okay. So now we have the situation where we have two sets of these. We've got translation A, scale A, rotation A, times translation B, scale B, rotation B, times the vector. All right? Now we already talked before about how to pull the translation out. You basically just scale and rotate the translation vector. It's pretty straightforward. So there you get, you can watch the previous video if you don't get this step, but we go translation A times scale A, RA, and then TB just as a vector, right? except then re-represent it as a matrix. We're just, whatever. It's, I guess, for the purposes of saying that, for the purposes of saying that the end is a vector, we can just pretend that we're treating this as a whole matrix the whole time, and just, we know that it's actually faster than that, okay? Because to scale and rotate one vector is very easy. So that factors out this TB. It moves it to the left. But then we have SA, RA, SV, RB times the vector, right? And the whole point of this, if you're confused about like, why would you break this off and multiply it out and keep this, why don't you move that? The whole point of all of this is that we compute this transform once and apply it to many, many vectors. So this translation is a constant, but this is we don't know what this vector is, right? We know what this is, and we know what all these things are otherwise. Okay, so let's put some equal signs or something so that we can pretend we're doing math. So that's equal to this. Well, so we want to turn this into the following thing. We basically want to swap the order of this scale and this rotation here. By the way, is my eye tracker visible? It kind of was not visible for a while. I can't really tell. I don't see it on the stream. This is weird. Oh, it's there, I guess? Is it? No? It's visible. Someone says visible. Okay, good. I restarted the program. I just don't know if it's actually working. Hard to see on dark green. Okay, we'll turn it up a little. Where did the program go? Is that more visible? How's that? So we want to basically, for example, you could think about this either way, but if we replace SB with some SB prime, right? Then, we get this SB on the other side of this, RA, and now we have rotations living together, we have scales living together, and we have translations living together, which gives us one of those new Xform state structures, right? Because these are all factored into each of their situations. Okay, so the question is, how do we do this? How do we swap the order of this R and this S? And it's actually very straightforward, right? So we want some situation where SB prime times RA equals RA times SB, right? If these two things are equal, we can swap them in. So we're starting some different set of equations than this one up here. So we just want this. And, well, how do you get that? Well, to solve for SB prime, you just multiply on the right both sides by RA to the -1. And I'm just going to say lowercase I. So often, like on paper, I might write exponent -1. But here, I'm just going to write RAI, actually, I for inverse, right? And that's, RA, I don't know, to the -1 or something, just notationally. Just caret -1 is kind of ugly. Okay. So you just multiply by both sides. So SB prime RAI equals SB RAI, right? RAI is just identity. Multiplying a matrix by its inverse gives you the identity. So this just gives you SB prime equals SB RAI. Now this is a pattern that you see all the time in computer graphics, is that you multiply something sandwiched between a thing and its inverse. Very common. Or a thing and its conjugate, right? So now, inverting a matrix sounds expensive, but actually, since this is a rotation matrix, it's an orthogonal matrix with determinant 1, which means its inverse is actually just its transpose. So I'm going to write RAT for rat. Transpose is a lot cheaper. You could just implement a transpose multiply and it just goes. That said, for quaternions, if this was a quaternion transform, this is just the conjugate quaternion, which is also a cheap thing to compute, but that's not going to be the thing here. So SB prime is RA, SB, RAT, right? So if we're going to do that substitution, then we'll pull this again, and we'll then say that means that this is RA, SV, RAT, right? So this is our breakup, and what this means is then translation is one thing. We're just saying what are the members of this struct now, right? The members of the result struct are like the following things, right? They're this, this. Wait, that's scale. Sorry. So the confusing thing is the members of the struct are written in a different order than how they actually live. So that might not be good, except for struct alignment purposes, it might. Oh, maybe not. Yeah, you get better struct alignment this way, slightly. Not now, but once we replace this by a 3 by 3. Oh, wait. Actually, you get better alignment by putting orientation first. I don't know. Okay, well, we'll make a comment about it. Anyway, so this is how that factors out. And so if we just do these things, then we can basically concatenate two transformations without going to 4 by 4 matrix and back. This is a little bit squirrely, right? So here, RA, SB, RAT is, in general, a 3 by 3 multiply, another 3 by 3 multiply, and another 3 by 3 multiply. That sounds expensive. First of all, though, just like we said, scale is like almost never gonna, gonna be anything but 1, right? Or, you know, if we know that the scale is diagonal, this simplifies in certain ways. If we know that it's a uniform constant, we could just factor it through. So we can have simplified versions of this routine. You know, we can switch off, you know, what kind of scale we know that we have in order to make it faster. So there's that. The other thing is, it's like, oh, this looks like a lot of multiplies, but previously all those multiplies were hidden. So for example, get matrix of an Xform state essentially has 3 by 3 multiplies in it. Although right now, because we only support vector 3 scales, it's cheaper. But the being confined to a vector 3 representation of the scale is where we got stuck before, because you can't, maybe you can. I guess you can. I guess you can do this with just a vector version of scale, because, well, we're going to try it and see if we get the right answer. Because when we go in here and we do our stuff, we can make sure that the result looks the same as what we got from this before we go ahead and delete this code and switch to this one. Okay? Does this make sense to everyone? Are there any questions about what we are talking about? Do games programmers ever use matrix libraries like BLAS, MKL, etc.? Do they normally roll their own? We usually roll our own. The reason is we don't need very serious matrix math usually. Like, we usually have small matrices for the common things that we do, like rendering and stuff. We have small matrices like 3x3 or 4x4. Our vectors are, 3x1, 4x1, or 1x4, whatever. And we want those specific operations to be compact and fast, which they won't be if we start using a generalized library. So that's a factor. Well, yeah, and we want to control our implementation and all of these things. These things are important. Something like BLAS is not thinking that hard about 3x3 matrix operations. Now, there is a different set of problems. Like, for the set of problems where it's like, I'm building some sparse matrix of constraints, and then I need to solve this arbitrarily sized sparse matrix, we might use a matrix library for that. We might also write it ourselves because we like to do that. But those are not, just to put textured triangles on the screen, we don't need to do that kind of a thing. That's a different problem space. It's not just about unrolling the whole set of multiplies, but there are SIMD instructions where it's like, hey, multiply all 4 of these things by these 4 other things, right? That we can just use directly, which, maybe matrix libraries would also use, but we know anytime you know your case very specifically, it enables you to do optimizations that other people may not be able to implement in their library because they can't assume that much about how the code is being used, right? So, yeah. Yeah, all right. Well, we're already doing most of this. So, we're already doing this part, I think, correctly, and we're already doing this part. The one that we don't have is the scale. And the thing is, I don't think I have prepackaged math operations to do this necessarily without blowing it up into a 3x3. So, usually I could do this first. So the rotation here, RA, is a quaternion right now. That's how we represent it. So this could be like a quaternion vector multiply. And then we have to right multiply that. I just don't ever write multiply that often. So it's annoying. And if I had code like that in the witness somewhere, I probably didn't import it to this game. So it may not be available. I could just convert it to a 3x3 and pull it out. Let's do that. So I don't even know if I have 3x3 math operations. So let's look at that. But if I just blow the scale up to a 3x3, then I can do multiply, multiply, and multiply. I can just do it super dumb and slow. And none of this should matter because we should end up with an identity matrix at the end of it because like all of our frickin' scales are identity. As long as that happens, well, we still don't know if we did it right because sometimes when you're multiplying identities around, you can screw up and still get the same answer. But if we didn't do it too wrong, we'll get identity out. So here's the funny thing is all the animation data that I showed you has identities there. Therefore, we don't really have good data for testing this end to end. So maybe after this code is done, I will have to ask the animator, hey, do you want to use some animated scale somewhere as a test animation? Okay. Let's look at the math module. So you have this set rotation on a matrix 4 for a quaternion, but not on a matrix 3. So I'm just going to do that. This is annoying. I've been thinking about compiler features. Whoops. Okay. So this is literally the same frickin' code. It's just going into a different memory layout. The text is exactly the same. So you could imagine some metaprogramming thing where you just say like, oh, this text comes from this other thing or something like that. Okay, so we don't even have matrix 3 defined right now. That's how much you know what? Here's the thing. So if I want to make this a little bit faster, I can go do all this stuff. But all these things, whoops, I thought this was the name of this buffer. It is. Nope, that's not the right one. Animation. Okay, all this stuff that we're doing, where I'm saying, hey, you could do this as a 3x3. You could also do this as a 4x4. It's just extra slow. But like what we're saying is this is going to be kind of slow anyway. So we can just do it extra slow right now, get this path working, and then we can if this out if the flags are not set, right? So these two parts of the code will work together. So yeah, let's just make it a matrix 4 operation and say, hey, we could actually make this be a matrix 3 operation. All right, so we're going to leave this note because that is relevant. We've got our translation. Our scale is going to be Well, we're going to say SA is in matrix 4. It's going to be identity. We're going to say okay, we're going to say, we're going to open a block and say speed. We are computing this in a pretty slow way, using matrix 4 when we don't need anything that big, but I didn't put matrix 3 into math. But in most cases, scale is identity anyway, so we don't even need to do this with proper annotation in the animation file. We can decide what to do here. Okay, so the goal is going to be to set SB by the end of this code, right? It's a little bit confusing. So this SB is not, these subscripts are not the same as these subscripts. Let's call it R for, C. C is going to be the outputs. And so we have A and B, except those are, we have C for child. I don't know, dude. Sometimes, let's call it G or O or, dude, sometimes you just can't win. Okay, I should have called these parent and child over here. I didn't. So now we're all confused. We'll call it global, meaning like global to the object. Because the letter G is pretty different from P and C, so it's easy to think about. So those are global. And we can print old way gives us this. New way gives us this. So we compare those and make sure they're good. Okay, so yeah, dude, I kind of just want to write multiply, but we're not going to do that. We're going to say SA dot x times equals, actually, let's just say SA is scale matrix of parent scale. SB is scale matrix of child scale, right? RA is rotation matrix of parent orientation. RAT is rotation matrix of conjugate of parent orientation. And then, okay, so SC is SA times RA times SB times RAT, right? So that's just this thing. Now this is scale as a matrix, so SG is V3 SC dot 11, SC dot 22. We're taking the diagonal elements out of that. And you don't assign this because we get it from above. Okay, so now we just have to write these helper functions. Okay, rotation matrix and scale matrix. So scale matrix is v vector 3 to matrix 4. Result, or let's call it R matrix 4 identity. R.11 times equals v.x. Return R, right? This is YZ, and this is 2, 2, 3, 3. So we're multiplying the diagonal matrix, the diagonal elements of the matrix by the scale vector to essentially convert scale vector up. Okay, and then rotation matrix from a quaternion is just, well, we have a helper function for that. We have set rotation. Yeah. We were just looking at that. Set rotation of R and the quaternion and return R. So there's that. So this is a big mess. And it is still going up to matrix 4, but which we said is what we want to avoid, but we can trivially knock this down to 3 by 3 instead of 4 by 4, right? 3 by 3 is 9 numbers instead of 16 for 4 by 4, which is almost half. So that's a halfway speed up. And then, of course, we can do optimizations on these things. But, so, for example, this matrix is just the transpose of this one. Maybe we can write them down and find some pattern that makes it faster, but even if we don't, then we could have a multiply by transpose function and just never compute RAT, just compute RA, and call multiply by transpose on this, and that would be the same speed as a regular multiply, right? So we would skip the creation of one of these matrices, for example. And then, of course, as we said before, if the scale is really representable as by a vector, that is helps us on a fast path. And if it's a scalar, that's an even faster path. So this is all good. I don't know. How bad did we mess it up? Well, it compiles. Well, old way, blah, 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 blah. New way, blah, blah, blah. Okay, so these two results are different in two ways, neither of which matter. So the first way is this orientation is oppositely signed of this one. You see that? So this has x, z, and w negative, and this one has x, z, and w positive with y negative. That doesn't matter because quaternions that are oppositely signed are the same rotation. The reason why this one got flipped is just because we're reading it out of a 4 by 4 and we're biased toward a certain half space of the rotation space when we do that. The other way this is different is just that our amount of math error in scale is slightly different. I don't think it's enough to matter. It's slightly more right now, but we're not going to worry about it because, like I said, we can do some things to factor this to be better. Anyway, but it looks to me like this worked the first time. Like, again, anytime you're messing with things that are identity, then who the hell knows? So we're going to have to make a test animation. But for now, I believe we could just get rid of this, right? And then get rid of this comment because that's what we're doing is we're concatenating Xform states directly. So there's our guy. He's still, oh. Rotation, okay, let's go to a different character. We changed the way our animation data is stored and we haven't updated everybody. And what that means is some of the characters are going to rotate funny until we do it for everybody. But for example, this guy turns to the proper direction and all that now because he's got the new data. That's a wholly separate issue from what we're talking about. So, well, so we changed the way we're doing this and it worked the first time. I don't quite like the way like he hops if I tap the keys like that. Maybe that's fine. Maybe I'm being too picky. It's like if you get the timing just right, he's like limping. But what can you do? All right. So it's working. Like what more can you ask for than when you do stuff like that and it works? Okay, the dancing injury was not my dance partner's fault. All right, let's make this clear. My dance partner was sterling and wonderful. What happened is when you go to places where a lot of people are dancing, some people do not have good spatial awareness. And especially if they're bigger dudes, this causes problems. So there was a bigger dude on the other side of my dance partner who like slammed into her and her head slammed into my head and caused this. And so it's not her fault. We can't blame our dance partner for these things. It's some random dude. And the dude was like, haha, oh, sorry. Like it was like a tiny bump. But I was like, dude, that was a lot of momentum. I don't think like when somebody has little enough experience to know how bad something was that they just did, then I don't know, you just like drop it at that point. You're like, okay, whatever, man. This hurt. That hurt real bad. So that's what happened there. Okay. Did I roundhouse kick him? No. No, we kept dancing. We're good. We don't want to let that spoil our time. Okay, well, that was going to be what I do for this whole stream. So that's done. We could... So we're going to take this out. We're going to take this variable out. We could do the 3x3 versions of all these just to have them in math. One of the reasons why I didn't put all this 3x3 stuff in the math library is I was all just paranoid about keeping code size small and compile times down. But at some point, if adding more and more code forces me to make compile times faster, then that's a good thing. So maybe that's what we should do here. Oh, here's the thing. So since I know this scale is diagonal right now, this right multiply is the same as a left multiply. So we could just... none of it matters because it's really identity. None of it matters. I don't know, man. We're going to want real data from the animator for sure to help with this. So maybe that'll be a fun stream. I'm going to be gone for the weekend, but after the weekend, we could do a fun stream with some kind of obviously scaly, stretchy thing. do the matrix 3 now. We could do that. Let's do that because we've got some more time. So we're going to need matrix 3 multiplies and all that. So let's just do these. Right, if we turn scale matrix and rotation matrix into returning matrix 3s, right, then everything automatically has to work. So we're going to need a matrix 3 identity. We're going to need set rotation, all this stuff. So let's go back to math. Set rotation on matrix 3. Bam. Did we have a matrix 3 identity? Whoops. So matrix 3 identity, going to matrix 3, no 4, 4. There we go. This is not even that fast of a routine. It doesn't matter. Like when we get down to micro optimizing this, it becomes different. Okay, so we have matrix 3 identity. We have set rotation. We don't have multiply, I don't think. All right. So we have matrix, vector, blah, blah, blah. Okay, this is matrix 4 by 4. We totally overload operators now. That, boy, that's an old comment. We've had operator overloading for a really long time. Okay, multiply m. Oh, wait, that's a matrix vector. Let's, where are our matrix multiplies? There we go. So we just replace the 4 by a 3. And that's it, I think. Oh, array bounds check failed. Oh, right. Sorry. These all 3s have to be 2s. Array bounds check failed. Oh boy. Okay. That wasn't what I expected. Interesting. Well, this is how the game is now, everybody. Okay, what did I screw up? It's probably here. Maybe it's in the definition of matrix 3. I didn't look at this very carefully. That looks, oh! Got to have the place direct. So that's the thing is I uncommented this and I was just, oh, this is fine, right? The point is this array representation of the floats is supposed to overlap in memory this, so that you can refer to them either way, which is what this place directive does. That wasn't there, and it didn't ever matter because we weren't using this because it was commented out. Guess what? It matters if you're using it. Place is not currently supported in unions? Oh, right. Okay, this is very old. Yeah. There we go. Oh, wait. What? 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 Okay, there we go. Look at the code. Look at the code and see what it does. There we go. Okay. I wonder if we have fixed rotations for some more of these yet. I could update. So there's still a few things wonky with the animation, like the character's still a little jumpy sometimes. He's still, like right there, he just 180 flipped without rotating through the angle. That's something that I have to debug, so that happens sometimes. When I first start up, there's some frame rate hitches because we load assets from text on demand, so those are going to have to be preloaded later. Yeah. So some of these, like this turning system is new from the past couple of days. The game used to drive turning of the character, and the animation used to have to try to match that turning, and that just wasn't a good way to do it. So now we let the animation drive the character's rotation, which is a little bit, you know, fraught with peril because the animations start out kind of relative, right? You don't want to have to make totally different animations for whichever direction the character is facing. So you have to apply them and then like add the relative angle. I don't know. Yeah. You basically have to treat root node motion from the animation seriously, but not too seriously. Otherwise, it'll cause bad things. And that might make other things questionable, like, you know, who knows if the foot position matching for animation switching is totally the way it should be and stuff. But anyway, that's everything I wanted to do on this stream. You know, that was a nice and easy stream. It was good action. It worked the first time. We like when things work the first time. And what more do you want? I ask. Is the T-pose wobble resolved? Yes, you can see us resolve that on the previous stream, which is now uploaded to YouTube. Will there be no animation instant movement option? Maybe. I mean, if people feel like that, it's a good thing. The reason we have the stuff tuned so, like, this is unrealistically fast, right? And the reason we do that is so you can go like 1, 2, 3, 4, 1, 2, and, you know, the controls are very tight actually. But yeah, you don't instantly end up in the square. So the question is, do we want to do more? Like, so right now we speed up time. Okay, here, if I just hold left or hold right, that happens sort of at a speed you would expect. It's still unrealistically fast, but it's not crazy. If I like tap right from here, 1, 2, 3, 4, 5, I go really fast, right? So that's kind of our concession to, like, you want it to look and feel good in 3D, but you don't want it to be interactively terrible, right? And so, like, if you know what you're doing and you're just popping around the squares, then it goes really fast. We can turn that speed up, and I guess we could make it instant. Yeah, those are all decisions to be made at the end of development. Is the keyboard input buffered? Yes. So let me think. This level is pretty simple, but let's go to this 2-character thing. So here, I can go 1, 2, 3 on the right and then switch characters and start going right, and it'll do it correctly. So yeah. Okay, that was a little bit weird because we loaded something. We loaded the sound effect or something, so we got a frame hitch. So let's do it again. I'm going to slam right 4 times, switch, and then start going right. See? So that character switch was a simple example, but it also works for using items and all these things. Let's slow down time a little. 1, 2, 3, 4, switch, 1. So See how my guy didn't start moving? So let's watch this again. Let's go a little bit faster. So I'm going to hammer 4 times. I'm going to character switch, and I'm going to start using my guy. When I character switch, he'll go into his active animation, which I think is weird and goofy right now. And you're like, what the hell is he doing? But he won't actually even start moving till after this other guy is done moving. Because this is a puzzle game, it's not supposed to have this kind of action challenge where you tweakily try to move your characters at the same time. We're just demonstrating robust buffering of the movement. So I'm going to go 1, 2, 3, 4, switch 1, right? 2, yeah. See that? Okay, let's do that again. Is 4, switch 4. So then what happens during gameplay is you know, that plays out much faster. But yes, in fact, let's do the whole thing. Let's solve the whole level. So 4, switch 4, switch 4, switch 4, right? So hopefully that'll solve the level. Yeah. So during a regular game, it's just like that, except at normal speed. Are those blue crystals missing textures? They're placeholder. A lot of graphics are placeholder. That wasn't a real puzzle, folks. This can't really be spoilers if it's this easy. The puzzle that introduces buttons on the floor is not really spoilerable. Is it possible to support skewing without making scale a 3x3 matrix? Okay, here's the thing. So if you're not talking about actual scale, if you're just talking about sheer absent of what you would normally think of as uniform scale, then those are the off-diagonal elements of a 3x3 matrix. They might even be, what's it called? What's it called when a matrix, oh, anti-symmetric. It might even be anti-symmetric. I don't remember. So it might actually only be 3 elements. We need to look that up and figure it out. A shear is also representable as a rotation, a uniform scale, and then another rotation back, I think. But by the time you're doing scale plus shear, you need to add back in those diagonal elements. So the question for me is it anti-symmetric or not? And the answer is, I don't know. I'd have to look that up. And it's hard to look up these days because there's so much weird, irrelevant garbage information on Google that I don't ever know what to do. Are the models used across multiple puzzles? Often they are, yes. In rare cases, we have one-off models that are not reused. How insane is the Witness Engine game going to be? It's going to be pretty insane. It's going to be pretty insane. When is morph keyframe animations preferable to skeletal? I think you mean like morph target animations or blend shapes is another thing that's called. I think those are roughly the same thing. Usually for something like facial animation, you probably would use blend shapes because like rigid body animations is not that good of a way to do facial animation. Because facial animation depends a lot on stretching and stuff like that. And you can do stretching in skeletal animation. It's just, I don't know. Like if for a face, you get into a position where you're like almost want one bone per vertex in the face. I mean, it depends on, of course, the polygon density of the face mesh. But once you start getting in that territory, then yeah, you use morph targets because it's super inefficient to have a skeletal animation do that. Are we going to soften the hard edges on the cast shadows? Yes. We're basically going to port the witness shadow system over to here. So they'll look like the shadows in the witness do. The thing is, we haven't done that yet, you know. Thoughts on Musk's interview yesterday? I didn't see it yet. Are the environments mostly 3D model in terms of the walls and stuff? I wish they were. That was my plan for how we were going to do this game, but the artists didn't want to do that. They threw a fit when I said that. Even though that's how a game like this would have been made for frickin' decades, they want to have lots of little things that they instance and blend into each other. And so, like, you know, that's a mesh, and that's a mesh, and that's a this level actually isn't that bad, but let me find one that's further along. I don't know, something like this, like each of these little flower things is a separate mesh. And so our renderer has to work a lot harder than in principle it should. Or we're going to have to do something where we combine all of these ourselves into our own set of entities. I don't really know. But yeah, from a programmer standpoint, you wish this was all one mesh, but it totally isn't. Like even this, it's like these are a couple of pieces. Yeah, very wasteful efficiency-wise to do things this way. But it's apparently how we had to do it. So yeah. Like each of these little fences is a little piece. And so forth. Will I ever release an FPS game? Not anytime soon. Maybe someday. Is this game totally rendered using OpenGL? What plan for release will use Metal for macOS? Yeah, so we're using OpenGL right now. That's mostly a temporary situation, though. In the long run, it'll just render using the native API on whatever platform we release it on. You could bake them after level design validation. That is true. But we would bake them as an automated process. We wouldn't manually do it. So, because you always want to tweak things, even in a patch or something. So we would like hit a button in the editor that condenses stuff down. It's not rocket science. It's just extra complication that we'd rather not have to deal with right now. Am I still planning on learning Vulkan? No, at this point, I've basically set the bozo bit on Vulkan. I'm not going to, because it's not the native API anywhere at this point. So why would I learn it? It's not the native API anywhere. And the point of it was to be the native low-level API. The point wasn't to be a glue API, but now it's trying to be a glue API. In other words, it has no reason to exist, actually. It's just making things worse. So no, I'm not going to learn Vulkan. Unless that change, like I could be wrong about this, but I don't know. So unless that situation changes, no Vulkan for me. All right, everybody, I have to go to the airport before too long, so we're going to end this stream here. But this has been good. Let's do our victory check. Oh, I just closed my Twitch window. Gee, if Windows made it any better to know which window was highlighted, like literally the difference between this being highlighted or not is like this 1 pixel blue border around the edge. Like in old Windows, the title bar used to change colors. They used to care about you knowing what was going on, but they don't anymore. So whatever, guys. Yeah. We're going to do our victory check-in. Whoops. We've got to check in matrix 3 stuff. Add matrix 3 stuff to math. Why do I have a tree? I don't want anything here. This was some kind of a update conflict or something, so we're just not going to check in any of that. And then here we're going to say animation player doesn't go all the way to matrix 4 to concatenate Xform states. Oh, before we check it in, we don't use set from matrix anymore, I don't think, which means we don't need case you get orientation, right? Which means all this stuff. Oh, we do. Oh, we do it when we're loading the file. So we could put all of this into sampled animation. Let's hold on. Let's do this. So, you know, eventually we're not going to be doing all this work that we do to parse the text file and to like do some of the stuff we did on the other stream, like record the footsteps and you know, translate into local space. Like all of that stuff eventually is going to be asset processing, so that when we load at game startup time, we just load a bunch of binary data that's already been processed exactly to how we want it, and that means that our game will start up a lot faster. So if the more expensive math lives in this file, that's fine, because it's going to get eventually invoked only at asset processing time. So let's verify we didn't break it. Okay. And let's redo this commit, because now we changed multiple files. Oops. All right. That's our victory commit. And thank you, everybody, for coming by. Oh, lines of code on the, well, we didn't really change the compiler. Sokoban is 865 whatever. Although, again, I'm not 100% sure that this number is right. We're going to have to validate this number at some point, because it seems to me like it maybe grows faster than the number of lines that I add. Maybe this is code that other people have been adding that I haven't been noticing. Let's do a really simple test. So we're going to compile. So 86527, and I'm going to say Foozle takes x as an argument, returns an int, and says return x times x times x plus x times x plus x, right? So that's a 3-line routine. It's got a couple lines of white space. I don't know. So now 86530, that's about what you would expect, right? X plus equals 3, 86531. Maybe it's correct. I don't know. I still want to validate it at some point. But yeah, that's how big the game is, apparently, including blank lines and comments.